Alright, let's dive right into this explainer and absolutely demystify one of the most intimidating yet absolutely crucial concepts in fluid mechanics, net positive suction head, or NPSH. Now, if you work around fluid systems, engineering, or industrial maintenance, you've definitely heard this acronym thrown around, and usually with a slight sense of dread, right? But today, we're going to break it down completely. We're stripping away the textbook jargon and translating it into clear, practical concepts so you can actually protect your equipment and keep everything running smoothly.
So picture this. You've just installed a brand new, wildly expensive industrial pump. I mean, everything looks perfect on the design spec. You hit the power, and instead of that nice, smooth, quiet hum you're expecting, it sounds like someone just dumped a bucket of jagged gravel straight into the intake. It's incredibly loud, it's violent, and you just know instinctively that if you leave it running, that pump is going to literally destroy itself from the inside out. But here's the crazy part. What you're hearing isn't gravel at all. What you are actually hearing is a destructive mechanical disease called cavitation. Basically, cavitation happens when the pressure of the liquid entering your pump drops so incredibly low that the liquid actually starts to boil at room temperature. It forms all these tiny microscopic vapor bubbles, but when those bubbles get swept into the high-pressure side of the pump impeller, they violently collapse. We're talking thousands of micro-implosions blasting away at the solid metal, causing severe pitting, massive vibration, and ultimately catastrophic failure.
Okay, so the big question, how do we stop our liquids from boiling inside the pump? Well, we have to monitor the system's vital signs, and the most important vital sign of all is NPSH, or net positive suction head. By definition, this is the absolute pressure head at the pump suction minus the liquid's vapor pressure head. But putting that into plain English, it is basically a measurement of how much pressure energy we have actively keeping that liquid in a liquid state, making absolutely sure it doesn't turn into those destructive vapor bubbles.
Section 1. Available versus required, the NPSH bank account.
To make this super intuitive, I want you to think about NPSH not as some crazy physics equation, but as a standard checking account. It's all about the money you have versus the money you need to spend. On one side, we have NPSH available, or NPSH-A. Think of this as the actual cash you have sitting in your bank account right at the pump suction. It is dictated entirely by your physical setup, your pipes, the tanks, the atmosphere. On the flip side, we have NPSH required, or NPSH-R. That's the minimum balance demanded by the pump manufacturer to keep your account open and avoid massive penalty fees, which in our case is cavitation.
Now here's the kicker. Your minimum required balance, your NPSHR, isn't just a static number on a spec sheet. It's determined by the specific pump design and the impeller type, sure, but more importantly, it changes based on how hard you run it. As you push the pump harder to move more fluid, it actually requires more energy just to pull that massive volume of liquid into the impeller eye. So the faster the flow rate, the greedier the pump gets, and it demands a much higher minimum balance just to operate safely.
Moving on to Section 2, the golden rule of pump survival. The fundamental rule of all this is incredibly simple. Your NPS available must always be greater than or equal to the NPSH required, plus a safety margin. Going back to our financial analogy, the cash you actually have in the bank must be higher than the minimum required balance, plus a little extra padded in there for overdraft protection, because the second your available balance dips below that required amount, boom, you hit cavitation.
But how much overdraft protection do we actually need? You definitely don't want to just break even. In standard, real-world engineering practices, a typical physical safety margin is usually an extra 0.5 to 1.0 meters of head. Or, if you're working on the initial system design, engineers will typically build in 10 to 30% extra NPSH available just to be safe, because let's face it, real-world conditions fluctuate, and that buffer is your ultimate insurance policy.
All right, Section 3. Let's actually calculate your NPSH bank balance. Let's figure out how to find that available bank balance without getting lost in the weeds. While the strict general equation does factor in velocity, taking the pressure at suction, adding kinetic energy, and subtracting vapor pressure, in most industrial liquid systems, the fluid just isn't moving fast enough for velocity head to really move the needle. So actually scratch the complex version. We can usually simplify it to the open tank equation, which you'll use like 90% of the time. You just take the atmospheric pressure pushing down on the liquid and you subtract three things: the static suction lift, the friction losses in the pipe, and the liquid's natural vapor pressure.
So let's build a mental picture of a real-world scenario and list out our initial deposits and withdrawals. Let's say we are pumping 25 degrees Celsius water straight out of an open tank. We've got standard atmospheric pressure pushing down hard on the surface of the tank. That right there is our initial massive deposit. But we have to pull the water 2 meters up into the pump. That's our static suction lift. We also have about 0.8 meters of friction loss from the liquid scraping against the pipes. And finally, the water itself has a natural vapor pressure at that 25-degree temperature.
Now, before we do the final math, we have a bit of a currency exchange problem. We have pressure measured in kilopascals, but we have physical pipe distances measured in meters. You can't just mix and match those. We need to convert the pressures into head, which is measured in meters. We do this by dividing the pressure by the liquid's density times gravity. So our standard atmospheric pressure converts perfectly to 10.33 meters of head, and our vapor pressure converts to a tiny 0.323 meters of head. Awesome. Now everything is in the exact same currency.
Next, we just balance the checkbook out loud. Step 1. We start with our massive deposit of atmospheric pressure, which we just found is 10.33 meters. Step 2. We withdraw our static lift of 2 meters because we have to physically fight gravity to pull the water up. Step 3. We withdraw our pipe friction loss, which costs us another 0.8 meters. And finally, Step 4. We withdraw the vapor pressure head, 0.323 meters. That's the internal energy of the liquid actively trying to boil it into a vapor.
When you do that simple math, starting with your atmospheric pressure deposit and subtracting all those physical and environmental penalties, you are left with an Npsh available balance of exactly 7.21 meters. Now, what does this mean? It means as long as your pump manufacturer says your specific pump requires less than, say, 6 meters, you've got a fantastic safety margin and you are completely safe from cavitation.
Section 4. System variables. What costs you money?
You really have to understand that every single choice in your system design is either a deposit or a withdraw. If you increase suction lift, meaning you place the pump way higher above the tank, your available head drops. If you use long, skinny pipes and increase friction, your available head drops again. What if the liquid gets hotter? Well, its vapor pressure spikes, which heavily drains your available Npsh. Conversely, a higher atmospheric pressure actually increases your available head. And fun fact, if you pump a less dense liquid, your head actually decreases.
Section 5. Actionable tips for pump survival.
So we want to maximize our available balance by cutting down on those unnecessary withdrawal fees, right? When you're designing a retrofitting a system, the rules are pretty straightforward. First, keep your suction line as short and as straight as possible. Second, use larger pipe diameters. Both of those moves directly reduce your friction losses. Third, avoid throwing in excessive fittings, elbows, and valves right before the pump intake. Literally, every bend in the pipe is a friction penalty. And finally, keep your supply liquid level as high as possible. Gravity is your best friend here. A higher tank drastically reduces your suction lift penalty.
But look, it's not just about the initial design. It's about your daily operations. A flawlessly designed system is still going to cavitate if it's poorly maintained. You absolutely must maintain clean strainers and foot valves. A clogged filter creates massive friction, choking the pump and sending your Npsh available plummeting. And of course, ensure proper pump alignment. And whatever you do, don't overspeed the pump beyond its design. Running it too fast artificially skyrockets the Npsh required.
To completely summarize the core philosophy of this explainer, always compare what you have to what you need. Cavitation is the immediate, highly destructive result when your available head drops below your required head. A higher available head guarantees a smoother, much longer life for your pump. And the biggest takeaway of all, your Npsh available isn't a property of the pump itself, it is dictated entirely by the complete system surrounding it.
Which leads me to ask you, when was the last time you actually checked the math on your own systems? Are your facility's pumps comfortably operating in the green, or are they running on a dangerously low Npsh bank balance, just waiting for one hot day or one clogged filter to trigger a catastrophic failure? Take these formulas, head out to your facility, and find out for yourself before that awful gravel sound starts. Thanks for learning with me, and I'll catch you on the next explainer.